Whistle, flash, thunder in the sky, blossoming chrysanthemum and falling stars, lighting up the summer night. The fireworks that you're seeing now was created with Blender geometry nodes. Today, I will be showing you how to make physics-based realistic fireworks using simulation node setup. Due to sheer volume of concepts to cover, like physics, spawning system, spark shader, I will be breaking the tutorial up into series. I am unaware of the total number of videos at the moment, but I am planning for it to be about 6 to 10 video series. It might be a lot to consume, but I'd appreciate it if you would stick with me till the end. Alright, let's get started. Alright, we'll hop right into Geometry Nodes layout. A to select all, X to delete. Shift A, add mesh plane. Go to front orthographic view using numpad 1 and 5. We'll also adjust the window's layout by dragging corners of pane so it suits a frontal view of launched fireworks. Next, click on New to add new Geometry Nodes map. Delete group input. Replace it with points. We will be performing most of the physics calculation on point basis, then later instance mesh on top of point. Alright, let's add simulation zone nodes. For anyone not familiar with simulation zone, left side of simulation input is initialization zone. Calculation is only performed in the first frame. Purple region is updating zone. Calculation is performed every frame and data can be carried over to the next frame. Right side of simulation output is post-processing zone. Calculation is done each frame, but no data is carried over. Here are the physics equations used for this tutorial. Position, velocity, and acceleration formulas. For position, we will be taking the previous frame value and adding the product of velocity and delta time. Similar for velocity calculation. For acceleration, we will be combining gravitational acceleration and drag deceleration. We will assume shell is launched like a cannonball and does not have its own thrust. Drag coefficient is that of a sphere, and we will assume sea level for air density. Okay, that was a mouthful, but I promise you after this video, you won't be bothered with formulas again. Alright, starting with a position calculation. We'll prepare a store named attribute, change the type to vector, and name it pos. We'll also add a set position node in the post-processing zone and plug in the named attribute pos. Next, duplicate the store named attribute of pos to initialization zone, and you can observe the point moving if you change the z value. Next, add a new store named attribute for velocity calculation. Name it vel and type in 1 for its z value. Retrieve the previous frame pos value by adding a named attribute. Duplicate the named attribute and change the content to vel. Scale it by delta time. Then add it with previous pos to get the current frame pos. Now, if you were to run the animation, you can observe the point is moving at 1 meters per second velocity. Let's also shorten the animation end frame. Select these 4 nodes and press Ctrl G to group them. Open up the side panel by pressing N, rename scale to delta time, then rename the node group to calc pause. Next, velocity calculation. After reverting to default value, let's duplicate the vel store named attribute to initialization zone. We'll also add another store named attribute to update zone and name it ACC. Once ACC is prepared, using named attribute to retrieve the previous frame vel, add it with delta time scaled ACC value to use it as a new vel. If you were to type in 1 into the value of ACC, you can see the point accelerating at 1 meters per second squared. Great. Just like before, select these 4 nodes, group them together with Ctrl G, rename scale to delta time, then rename the node group calc vel. We'll do some rerouting to keep the node map clean. You always want to make sure you can see what's going on. So with this setup, you can simulate freefall if you were to plug in the gravitational acceleration of negative 9.81 meters per second squared. Lastly, for acceleration, we'll pull out a value out of store named attribute and rename it AG. Next, let's start on drag deceleration. We'll prepare 2 new attributes for this calculation. First is mass. Let's add another store named attribute with float and name it mass. Another is radius to calculate the cross-sectional reference area. Though we can use point radius, we'll use a store named attribute to hold its value instead. Let's call this rad. Input 0.1 for both. Alright, let's start with the equation. Start with named attribute of vel. Use vector mass lengths to get its magnitude. Then square it. Next is a cross-sectional area. This is simply pi r squared. Multiply these two results. Then, multiply by the sphere drag coefficient, 0.47. Next, multiply by the air density rho. 1.293 kilograms per meter cubed. Divide by 2. Then divide by named attribute mass to result in magnitude of drag deceleration. To get the directional vector of drag, we'll duplicate the vel and normalize. Since air resistance acts opposite to velocity, we'll then scale it by -1. Lastly, we'll scale it by the magnitude we just calculated previously to get the drag vector. Alright, I'll just frame these. Let's add the gravitational acceleration and drag deceleration to get total acceleration. We'll group these nodes up and call it Calc ACC. Then reorganize. We can see the added effect of drag when we were to run the animation. Let's try increasing the radius without changing the mass. Think of a balloon which has high volume and low mass. Free fall of this object looks like this. Acceleration halts due to its low terminal velocity. Next, let's increase its mass and decrease radius. Imagine a tiny metal ball. Dropping this will result in high acceleration with small drag. It will not reach terminal velocity with this short animation. Alright, this is it for physics. So before we wrap it up, let's input some actual shell data and see how it launches. Though physics should work with any value, I'm going to use this real-life size 5 shell as a reference. According to this data, it has 15 centimeter diameter, 1.3 kilogram mass, and reaches about 195 meters in height. Let's input these values into store named attribute of initialization zone. For initial launch velocity, 100 meters per second seemed to be a good number. Okay, let's try launching. Alright, it just bolted off screen. We need to zoom out quite a bit to fit 190 meters into screen. Since we're not going to be able to view the point, I'm going to tentatively put an icosphere on top. Let's add an instance on points after set position and instance of icosphere. Now we can see it. The grid is 10 meters in height, so it is launching up to about 195 meters. We can see the shell falling if we change the end frame. Alright, that is it for this video, so let's review what we just made. Please check any connections and data settings if it's not working correctly. This is the overview. Next, for the acceleration. Next, velocity. Lastly, position calculation. For the next video, I will be going over how to create burst and spawning system. Thank you for watching, and see you next time.